having seen the computer industry, we have witnessed 3 computational revolutions already. And each time there has been a computational revolution, not many people have really understood it. When I was growing up, pretty much the PC era was already embedded. But if you look through the hindsight, the reason PC era has been so enormously successful is predominantly for 2 reasons. Number one was that you could now, for the first time, go and buy software in a retail outlet. Number 2, the entire ecosystem of supply chain came together and kept making the systems better and better and better. These were the 2 fundamental reasons why PC era could reach over 1 billion people. Soon after that, it was about connecting mobile to the internet. It was a very myopic focus for people to bring technology that could connect to internet. And Qualcomm has a lot to do with it. What they ensured is that we could get the power of internet onto the mobile phones, but more importantly, in addition to what they did, was the availability of this little application that resides on your phones, gets connected back to the internet, and brings joy. And this reached over 3 billion people. And then somewhere, in our ability to keep building data centers and having massive amount of resources that needed to be with us, there was a company that changed the whole business model of data centers, Amazon. I believe they're also speaking today. For the very first time, you could now go and rent a data center. You did not need to spend money on buying computing. You could now invest money on human resources that you could deploy even as a startup. It was a change of a business model. Through these phases, each time there has been a revolution, it's an opportunity to have a new company emerge. Some of these new companies then become big companies, and they blossom. And today we are talking about the dawn of a new era. The AI. And it's absolutely clear to everyone that this is going to be bigger than anything that has ever happened. And the reason is, for the first time, software will write software. Computers will learn. Machines will eventually become autonomous. Think about it. Reflect back. The history of mankind, automation has been in center of every single invention. Farming automation was about food production. Industrial revolution was about power. Now you are in the era of automation of automation. And if you look in that context, this is an opportunity for each one of us to do what we could have never done, to solve problems that were never solved. Therefore, this is a new computing era with brand new tools. So I'm going to attempt and talk to you a little bit about what are these tools, what are we really talking about, how does it really work, and how can it benefit all of us. The word AI, machine learning, deep learning, more often than not, gets used interchangeably. More often than not, I get to hear the word AI, ML. Predominantly, people believe that deep learning is a smaller component, but the fact remains this whole revolution that you're hearing around AI is currently happening because of deep learning, and we'll talk a lot more about it. But look at that chart. AI is the bigger picture. If I have to define AI, it is nothing but the automation of human intelligence that is deployed by us into machines. Now, that's a very tall order. Bringing all our intelligence into machines is a very tall order, and scientists have been trying to work on this since the 50s. And what they initially achieved was predominantly what we call as classical programming. What they felt was that if we took really smart programmers and gave them large set of rules, they could manipulate knowledge. And one way of looking at that is through that little box that you can see where rules or programs in conjunction with the data are poured into a box and out comes your answer. Right? That's how we do it. It has solved many logical problems. It's still in implementation, and it really works even for games such as chess. But it really is untenable the moment you look at fuzzy and complex problems. Problems such as image classification, speech recognition, language translation, it refuses to work. People even called it narrow AI, symbolic AI. And around 80s, there was a need for really to look at machine learning. But what people felt is that why can't machines look at the data, formulate a rule on their own, and output an answer? One of the easier ways that I figured out how to look at this is like this. So instead of putting rules and data together into a box that will give you an answer, why don't we take a data of which we already know the answer, put it inside, it gives you a rule. Next time when you have a data, you apply that rule and you get a new representation of the new data. It's automation. Now, what does it really require? It obviously requires an input data. And where do you get your input data? If you want to do speech recognition, you find it in the transcript files. If you want inputs on photographs, you find it in your photographs that you have tagged. Right? You can also, after that, you basically have the answers. You already know this is Vishal, that's Vartika, that's Shweta. And you start telling them that. That becomes the output answer to it. But at the background, between that output and the input resides a feedback signal that tells you whether the answer is exactly right or further from the right, which happens through a feedback signal. Therefore, machine learning is nothing but looking at the representation of data in an automated way within a prescribed space that gives you insights into the information that data contains. And it was around 2010 when a new trigger really started off called deep learning, which has created this huge wave. This entire noise that you're hearing is because of deep learning. And deep learning is fundamentally different. It is a subset of machine learning, but it approaches the problem through neural networks. What it does is that it occupies layers upon layers upon layers upon layers, and each layer is an input to the next layer, and distills information through that, through which we get the possibilities of hierarchically creating knowledge. Let's have a look at that. So let's assume there's a face. How will computer really understand if you have to automate the entire process? That's a face. It will start from the first layer, understanding the edges and contour, get to the next layer that there is an ear, there's a eyebrow head there, then go and build the shape, and then eventually reach a level where you can find the face. Now, what deep learning has done is that it's made it really simple. It is so simple that you don't need to be a domain expert to use it. You don't need to be a hard-coded programmer who will write very heavy pipelines to do it. That's why there's so much of popularity in it. It's extremely versatile. It's versatile because you can use this algorithm on multiple things. So if you use an algorithm in healthcare, you can probably use it in autonomous vehicles. You can reuse it. And it's extremely scalable. It is showing to us that in a lot of places, especially when it comes to image and speech, it is crossing human efforts. You're talking about superhuman levels that it is crossing, 97%, 98%, 99%. And that's the interest behind deep learning. Now, there's something that's happening in our industry. In our computing industry, there are two fundamental governing forces that are working in clash with each other. The first one is software, which is deep learning. As we spoke about it, deep learning is fantastic. It can take representation from one layer to the second layer, arrange it hierarchically, understand what's inside it, distill knowledge, distill and predict what needs to be done, and makes it even very, very prescribed. But it has one large handicap, and that handicap is computation. It requires tons and tons of data that needs to be fed and requires humongous amount of computation. So a lot of us connect deep learning with autonomous vehicles. You saw it in the video. A human in a year covers 1 billion miles each year. If you really want to make an autonomous vehicle to replace a human being who drives it, obviously you require billion hours of data that needs to be fed. Where are you get billion hours of data to be fed on a computational power? It has to be on the microprocessor. And this problem is happening exactly at the same time when the Moore's law is challenged on microprocessor. Never ever in the history of mankind have you ever seen improvement on one thing over 1 million times. Microprocessor, the CPU, had performance improvement of over 1 million times in last 30 years. It would double every 18 months. And suddenly, in near times, now you're talking about 10% growth. So you're talking about Moore's law that can take you 10% up, and you're talking about a huge computational challenge. It's not because the device physics can't produce more transistors. The blue line shows you that. There's enough that we can produce transistors, but our techniques of creating parallelism, Dynat scaling combined with that is stalling the growth of the microprocessor. And this is the time when new computing model is emerging in front of you. We call it the GPU computing model. It wasn't as if GPU computing model was introduced today. It's been simmering for 15 years, but its timing is right now. Now for developers and for teachers here and for students who are probably sitting here, you will well appreciate that if I have to endorse a platform, it's not easy for me to endorse a platform because I need a platform. This is extremely pervasive. And if I'm going to adopt a platform, there has to be gigantic performance increase in that. If I need a platform, it should last for years. If there's a platform, it should have an application that can reach everyone. It's almost like a tug of war between an application guy and a new platform. That's why, ladies and gentlemen, you often don't see a new platform emerging. However, the GPU computing platform, on which I'll take a minute to explain to you, gives you a performance when augmented from the CPU 50 times in certain applications, especially in deep learning, high-performance computing. GPU computing came into play for computer graphics. It is a high-performance computing problem because via computer graphics, you are trying to synthesize virtual worlds. If you have to synthesize virtual worlds, you obviously require computing powers which are near what God would like to give to you. If you look at the libraries that have been available on that, we are in its 10th generation. We solve computer graphic problems. We've taken high-performance computing problems. There are about 500 applications that get accelerated with that, and that's the reason people are looking at endorsement and now AI via deep learning. The scales are completely different. We talk about pervasiveness. You can look at GPU in a cloud and you name your cloud. You may decide that, hey, in addition to cloud, you require it in data center. It's available from every single OEM you can think about. You might decide that I want to use it on my laptop. It's available on my laptop. So you can start with GPU computing pretty much now if you haven't really done it. There's no debate in anybody's mind that next 40 to 50 years is GPU computing. So please get used to the word GPU computing, throughput computing, parallel computing, because if AI is going to make a difference, it's going to be via this. Let me share with you some of the research work that's happening in this area, and I'll connect 3 examples that how AI is able to do it. In my first example, if you look at these 2 pictures, it's about ray tracing. And some of you who understand ray tracing, it's nothing but each light or each photon, how it hits the surface and comes back to your eye. And when you're filling that in a computer art, it leaves those sparkles that you saw on the left side, your left. Now, think about a movie being created. It takes hours to render it. And you're left with that, and humanly you have to go and fill all of them so that it looks more realistic. Think about a game which is real-time, interactive. If you will leave black dots there, what's the fun of playing a game? And through AI, we made an announcement day before yesterday, RTX, real-time accelerator. We are doing it in real time, what you see on your right side. And this is a little older demonstration, what we've been exhibiting since yesterday. You're doing it 60 times more per second faster now because of that. So think about your movies. The time to build them will come closer. Your entertainment will become faster. Think about the games. You can do it faster. Now think about how you can apply it in your lives. It's AI combined with traditional computer graphic techniques. Next example.
Listen up. The train yard warehouses is our main objective. Alexei, you and your men will do that. You have to go in and out very quick.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
The avocado is a pear-shaped fruit with leathery skin, smooth edible flesh, and a large stone.
What is this? This is facial animation, right? It's exactly opposite of lip sync. We typically learned that we can see somebody's lips and recognize the words being spoken. Now you got to apply words to the face. Think about the applications that can be used for that. As robots will come together, as you guys will make people work together, all those things can be realistically targeted. My colleague did a fantastic thing. If you go outside and see, the same language is being spoken in Telugu with the same expressions, same words. Have a look outside. This is a demo which is from University of Edinburgh. It's a character animation. Look at it. He already knows where to walk. He can turn around. He knows that there is a danger there, takes a right turn, and moves. That's how your robots are going to work. You know how difficult robots take to make it applicable. They can do one thing at a time. Here he's almost walking like a human being. Get your imagination fired up. It's all because of deep learning. Every single demo that I've shown you is about deep learning. Now, deep learning sounds really easy. But deep learning is extremely difficult to deal with because it requires data, computational power, algorithms, and you require lots of cobbling that to take place. What we call as the learning phase of computers. But deployment is even more difficult. Each one of you, and let's take all Indians, there are 1 billion phones. Now, if X number of billion people need to just find out at the same time what's really happening at Chola, at ICT, ACT, Bridge, it would require you a data center of that nature just to respond to you in the time that's acceptable to you. If you're talking about autonomous things, everything that moves will be autonomous. That's 100 millions of them. And this word called IoT, sensors, they're going to be in trillions. And you're going to go and deploy what you've trained is on those end devices. People are making it very trivial. People are making it so trivial, saying that, oh, running something small, I don't need something really heavyweight. Computationally, I can run it there. The reason I say that is because your neural networks are getting complex day by day. Your computer vision, CNN networks, sequential ones, recurrent networks, the new age networks called the GAN, where there's one good network and one network to fool the other, fighting against each other. You're talking about reinforcement learning. There's complexity and complexity in this neural network. This is another way to look at it. 2012, AlexNet beat the best ImageNet competitor by 10 basis points. In just 5 years, this complexity has increased by 350 times. In fact, if I was to update this chart today, it's about 500 times. That's the level of complexity, the depth, the insight, where you want to do, how you want to do, how do you build it, how do you tweak it, where does it really work. The speech algorithm, where the Baidu speech 2 was literally giving you 97% accuracy, has gone up by 30 times. The translation parts are again going. So the complexity as mammoth, so are the devices, and so is the network. So how are you going to deploy it? You train big, you unfold what's not required, you understand the character of it. Not everything is most critical. Car is very critical, but is the thermostat, which is going to tell you that little disturbance that's going to take place in your furnace, as important? Or something which will test out and tell your heartbeat 2 seconds later, is that so important? Has different characteristics. So you need an inferencing framework which can unfold unwanted and just provide the right input to the right characteristic depending upon the accuracy that it requires. So you require a programming model like this. Let's have a look. So if I take a CPU, and all of you are familiar with CPU, and I take the latest, the greatest CPU, if I start finding out through a satellite or an aerial view about a city, and if I want to label what is really there, which is a building, which is agricultural land, which is a park, which is a intersection, this is how it will do, and it will give you a really good output. You will get 4.7, let's say 5 images per second. If I take GPU and I just run it on a single GPU, I will do it approximately 500 times. And that's only one at a time. I take TensorRT, and I put it on 8 GPUs. This is how it will look. Near linear times. What 1 was giving, that's what 8 is giving, and that's how your training and your inferencing really works. What does it really mean, Vishal? That's what you're asking. What does it really mean? From a computing angle, this is what it means. That if you build a center for inference to do a problem like this, in this example, they've taken that, hey, you want to look at 45,000 images per second, you will end up building a 4-rack data center. It's going to be 65,000 watts. I guess you'll say, then you build it with the GPU. 1/6 the cost, 1/20th the power, and in 1 rack. You didn't get it, right? With CPUs, with GPUs. What do we call it? Save money. You truly save money. The more GPUs you buy, the more money you save. In fact, what you should be saying, Vishal, I'll buy more GPUs, we'll save money, let's do more business. I'm going to come towards the end of my conversation. We're all talking about autonomous vehicles. We have our own opinions about autonomous vehicles. When it comes to India, we shied it by saying, hey, the day autonomous vehicles can work in India, we would have achieved. But it's not about autonomous vehicle, but look at the technologies that go behind it. Let's do it with a quick video. So it got to know its surroundings, right? So if you have some machine which is going to act like human beings, you better know what's happening around it. You got to figure out that what is moving around you, and you got to understand that what action you need to take. You saw in the example first also that the lady was trying to open the door. If the bike was coming, it stopped. It won't allow the lady to open the door. To protect it. Likewise, you need to understand the lanes. And lanes, etc., cannot happen through sensors or cameras or through LiDARs. Everything needs to be fused together. You need inputs from even your instruments. That's real complexity that you and I go through. Now you're going to put that into autonomous vehicle. It's not about autonomous vehicle, it's about your joy of sitting in that autonomous vehicle. Will the vehicle really have a steering? Probably not. Do the seats need to face the window, or shall it face around us? Can 4 of us sit together and have a conference call? Can we basically have the screens where we can even write, just like we can write on any of the screens? That's the possibility. In the Amazon click era, how are we going to do the planning? This is how it's going to be solved. Okay? Imagination, think about it. We can go on about it. I can see the timer doing it. This is exactly how the autonomous vehicles look like today. You open a boot, CPUs, GPUs, all put together, 30,000 watts, and the car hasn't even moved. A car moves for about 10 hours, that's 300,000. Battery life, 100,000. So how is it possible? It's only possible if somebody does this. That's 320 tops, and we are talking about, how much is the power? We're talking about 500 watts, and we have to still bring it down to 50 and 30 and 20, and it's only number plate. It's only number plate size. I'll show you. Actually, I've got $4 billion in my pocket. This is the data center. Thousands of engineers spent billions of dollars to build it. It's the world's largest processor, 21 billion transistors on this, right? It's got CoWoS, 12-FINT, and more importantly, memory which is stacked on top of that. So few billions go on to my right pocket. If I use the car, the little sibling, 9 billion transistors on that, and it makes your car run. That's another few billion. So I'm actually very rich. If you steal me, it's very nice. That's the power of GPU computing. So we'll now try and basically close the summary based on the timing. I didn't have enough time to tell you everything. But you look at computer graphics. You don't need to really visit every showroom. The showroom will come to you. You can interact with your CAD designs. You can interact with your vehicles. You can change the color. You can position it. You have every single tool in GPU computing to make it possible today for you. And more importantly, you save money. And we spoke about it. You save money each time that you buy GPU. So what does it mean for education? For education, it means create center of excellence. We will work with you on grants. We will work with you in bringing you teaching modules that will come from the finest and the best people who have created deep learning. NYU, for example. You can have the whole elective. You can have the whole modeling. We'll work with you. We'll bring you the best speakers together. This is your opportunity. Give it to your students, because a student, if you're going to only train him based on sequential writing, may not be worthy of a career if he can't think about it in an intuitive way, in a thinking way, and we have a challenge. So it's almost on you that you need to create deep learning center of excellence. And some of you who are developers, please go to these sites, have a look at them. All tools are available. All of us are here. Demos are in place. Come and talk to us. There are few of us here. Some of them are sitting on this side. There are demo booths outside. I think the opportunity is India. India needs to be in its glory. India needs to move away from a sequential thinking into parallel thinking. Today is our time, and the good news is it's not late. We are pretty much there. Let's make it happen together. Thank you very much. Enjoy the rest of your conference.